What if I told you that the secret to building the next generation of super smart AI
Yeah.
is actually teaching it to actively ignore its teachers?
Wow. Okay, that's a bold claim.
Right, because usually when we think about training an artificial intelligence, we rely on this, I don't know, this highly romanticized idea of perfect knowledge transfer.
Like the master and the apprentice.
Exactly. The massive, brilliant AI master shows the exact path, and the tiny apprentice just copies every single movement perfectly.
Right, right.
And eventually, the apprentice achieves mastery. It's a very comforting, linear concept of learning.
It is comforting, but, well, it relies on a pretty massive, flawed assumption.
Which is,
It assumes the master is completely infallible. Right.
Ah.
Even worse, it assumes that the apprentice's only job is to be a perfect, uncritical mirror.
Which, I mean, works great in a martial arts movie. But
Yeah.
when you look at the absolute bleeding edge of generative AI, that perfect mirror just shatters completely.
It really does.
So welcome to the deep dive. Today we are looking at a state-of-the-art foundational paper that is fundamentally changing how we approach Gen AI architecture.
This is incredibly relevant for you, the listener, because, well, we're talking about the core mechanisms that will dictate how the AI tools you use every single day actually reason.
Exactly. So we are diving into a brand new research paper titled Reward-Gated On-Policy Distillation, or RGOPD.
RGOPD, yeah. And this comes to us from a powerhouse team of researchers. We're talking University of Cologne, AWS AI, UT Austin, and MIT.
Heavy hitters. Okay, let's unpack this because this paper is the perfect shortcut for you to stay completely well-informed on where AI is heading.
Without having to, read a dense 50-page academic PDF.
Exactly. I'll pass on the PDF reading. So the core mission of this deep dive is to decode how this new filtering technique changes AI training from the ground up.
Right.
We are going to explore why unconditionally trusting a teacher is actually a recipe for disaster in the machine learning world.
It really is.
Our goal is to understand exactly how researchers are teaching smaller, highly efficient AI models to reason like the massive, astronomically expensive ones.
But without inheriting all of their flaws.
Yes.
Which is such a critical framing. I mean, it's incredibly easy to get swept up in the magic of these massive foundational models.
Oh, totally. The trillion parameter behemoths.
Right. But if we connect this to the bigger picture, this research reminds us that critical thinking is required even for algorithms.
Yeah, we can't just have blind faith in a giant model's outputs.
No, we can't. And more importantly, we cannot mathematically teach smaller models to have that blind faith either.
Okay, so to really appreciate the genius of what this RGOPD paper proposes, we need to set the stage.
Makes sense.
We have to look at how things are currently done and exactly where that standard process falls apart. Let's talk about the current industry standard.
Okay.
Right now, to train a smaller model, which we call the student, we use a technique called on-policy distillation, or OPD.
Yeah, standard OPD.
Right, let's break down what that actually looks like in practice.
Sure. So in a standard OPD setup, the smaller student model is given a prompt or a problem, and it generates its own reasoning steps.
Okay.
It tries to find its own pathways to solve the problem. In machine learning, we call these pathways trajectories.
Trajectories, got it.
So the student is actively generating a trajectory. But while the student is doing this, the massive teacher model is watching.
And it's not just watching casually, right? I mean, it's heavily involved.
Oh, very heavily involved. The teacher provides dense, token-by-token supervision on the exact states the student is visiting.
Token by token.
Yeah. What that means is the teacher is evaluating every single step.
Yeah.
Every single generated word or symbol in real time.
Wow.
It's calculating how likely it would have been to generate that exact same token itself.
Okay, let me make sure I'm picturing this correctly for the listener.
Go for it.
Imagine a high school student doing a really complex multi-step calculus problem on a whiteboard.
Okay, good visual.
And standing right behind them is a genius, world-renowned tutor leaning over their shoulder, aggressively whispering, yes, yes, no, yes, for every single stroke of the dry erase marker.
That is a highly accurate analogy.
So every single number, every single symbol, the tutor is weighing in on how likely they would have been to write that exact same thing.
Exactly. And that token-by-token feedback from the teacher is what we call logits.
Logits.
Right. Logits are essentially the raw mathematical probabilities the model assigns to different options. So the teacher is providing a logit distribution for every single step.
Okay.
It's an incredibly rich, dense learning signal. It tells the student exactly how to adjust its behavior at a micro level to act more like the genius tutor.
And historically, this has been highly effective, right, compared to just, giving the student a pass or fail grade at the very end of the test.
Absolutely.
It sounds great in theory. You have a genius guiding every stroke of the marker. But, and this is the massive flaw the researchers zeroed in on, this standard unconditional OPD approach has a fatal assumption built into its core.
The infallibility assumption.
Exactly. It treats the teacher like an infallible oracle. It assumes the tutor whispering in the student's ear is always universally right.
Which, as anyone who has spent more than 5 minutes working with large language models knows, is simply not true.
Definitely not true.
Teachers, even the most massive 70 billion or trillion parameter models, they make mistakes, they hallucinate, they get trapped in flawed logic loops.
Right.
And standard unconditional distillation forces the student to mimic the teacher no matter what.
Because it's just matching the probabilities.
Exactly. The math of unconditional OPD demands that the student's probabilities match the teacher's probabilities. And this creates two distinct, very dangerous failure modes.
Let's really dig into those failure modes, because this is where the blind mimicry breaks the system.
Yeah.
What happens in the first failure mode?
So the first failure mode is when the teacher endorses a student failure.
Endorses a failure.
Yeah. Let's say the student goes down a reasoning path that sounds highly plausible, it used all the right jargon, it sounds confident.
But mathematically or factually, it's utter nonsense.
A classic AI hallucination.
Right.
Now, if the massive teacher model also happens to suffer from that same blind spot, which happens frequently because they are trained on similar data,
Oh, of course.
the teacher looks at that nonsense trajectory and assigns a high probability to it. The teacher essentially says, yeah, I would have said the exact same thing.
So standard distillation takes that signal and tells the student, great job, do more of that.
Exactly. It artificially reinforces a bad habit just because the teacher shares the same bad habit.
Man, so it's the blind leading the blind.
It really is.
And because the teacher is so confident in its wrong answer, the student permanently bakes that hallucination into its own neural network.
Yeah, it's actively learning to be wrong.
That is wild. But there is a second failure mode that I find almost more tragic.
The suppression of brilliance.
Yes. This is when the teacher actually suppresses brilliance.
Right, so this happens when the student naturally stumbles upon a highly efficient, novel way to solve the math problem.
Okay.
It's a completely correct trajectory, but is one the massive teacher model would never have taken itself.
Because it's not the standard way.
Simply because it falls outside of the teacher's typical patterns. Yeah.
So the student writes a brilliant shortcut on the whiteboard.
But in unconditional distillation, the teacher looks at that novel, brilliant path and assigns it a very low likelihood.
Not because it's wrong.
But because it's unfamiliar. The teacher essentially tells the student, don't do that. I wouldn't have done that.
So the genius tutor just slaps the dry erase marker out of the student's hand because they didn't do it their specific way.
Pretty much.
Even though the answer was completely right. So unconditional distillation actively erases useful, correct student behavior just because it differs from the teacher's style.
Which tells us something crucial about machine learning. A dense learning signal is entirely useless if it's pointing in the wrong direction.
Yeah, that makes so much sense.
The teacher's feedback is powerful, but it is absolutely not inherently reliable.
Which brings us right to the core innovation of this entire paper.
The gate.
The researchers realized that blind mimicry fails. So there needs to be a mechanism that tells the student exactly when to listen to the teacher.
And when to just tune the teacher out.
Exactly. And that mechanism is what they call the reward teacher gate.
The elegant solution here is introducing a third party into the loop. A verifier.
A verifier.
Right. A verifier is a completely separate mathematical mechanism that only cares about one thing. Did you get the final answer right or wrong?
Okay, so it ignores the middle stuff.
Yeah, it doesn't care about the steps, it doesn't care about the vocabulary, it just looks at the final outcome and assigns a sparse terminal reward, pass or fail.
Okay, so going back to our classroom whiteboard analogy,
Yes, let's do it.
we have the student at the whiteboard generating the steps.
Yeah.
We have the genius tutor whispering in their ear about every single stroke of the marker.
Right.
And now we have a stern examiner sitting at a desk at the very back of the room.
I like it.
And this examiner only looks up at the very end of the problem to say, correct or incorrect.
That's a perfect way to visualize it. And the RGOPD system, the gate itself, sits between all three of them.
Okay.
This gate evaluates the situation before letting the student update its internal network. It only allows the student to actually learn from the teacher's token-by-token feedback if two very specific conditions align perfectly.
And those conditions are?
First, the final answer has to be right or wrong according to the verifier at the back of the room.
Okay, that's condition 1.
And second, the teacher's preference for the steps taken has to logically align with that final outcome.
Okay, hold on. Let me just pause here. I need to push back on this.
Sure.
Because I know what you, the listener, might be thinking right now.
What's that?
If we already have this stern verifier at the back of the room who knows with absolute mathematical certainty whether the final answer is right or wrong, why do we even need the teacher at all? If the verifier knows the ultimate truth, let's just use the verifier, fire the expensive teacher, and let the student learn from the verifier's feedback. Why go through the computational hassle of comparing the two?
This raises an important question, and honestly, it's a completely logical pushback. In fact, it's exactly where many pure reinforcement learning approaches get stuck.
Oh, really?
Yeah, the logic of firing the teacher makes sense until you consider the reality of how these large language models actually learn.
Okay.
Remember what we said about the verifier?
Right.
It only gives a terminal reward. It only gives a pass or fail at the very end of a massive chain of thought.
Right.
So if you generate 1,000 words of complex reasoning and fail, the verifier just says wrong.
Just wrong.
Yeah. It provides zero information on which of those 1,000 words was the actual mistake.
Oh, I see. It's like getting an F on a 20-page term paper, but the professor didn't leave a single red mark in the margins.
Precisely. You have no idea what to fix for next time.
Yeah, you don't know if your core thesis was deeply flawed on page 1 or if you just made a tiny arithmetic error on page 19.
Exactly. The terminal reward is just too sparse. It takes millions of trial and error runs for a model to learn from sparse rewards.
So the teacher is still useful.
The teacher provides that dense, red ink feedback on every single word. RGOPD is brilliant because it perfectly bridges the sparse verifier rewards and the dense teacher logic.
Yeah, I get it now.
It uses the verifier to decide whether the trajectory is good overall, and it uses the teacher-student likelihood gap to decide what exactly needs to change step by step.
Okay, that clicks perfectly.
Yeah.
So let's look at how this gate actually operates in practice. It seems like the gate only opens in 2 specific scenarios.
Right, 2 scenarios.
Scenario 1. The verifier says correct, and the teacher model actually liked the reasoning path more than the student naturally did.
Exactly. In that case, the gate opens, and the system says, good job, you got it right, and the teacher knows exactly how to help you solidify those good steps for next time.
That's the positive reinforcement side.
Yep. And then there's scenario 2. The verifier says incorrect, and the teacher model assigned a lower probability to those steps than the student did.
Okay, so they both agree it was bad.
Right. The gate opens again, but this time it says, you failed, and the teacher actively disliked what you were doing anyway, so let's use the teacher's dense feedback to learn how to move away from those specific bad steps.
But in any other scenario, say the student gets it right, but the teacher hated the novel steps.
Right.
Or the student gets it wrong because of a hallucination, but the teacher loved the steps. The gate just slams shut.
It slams shut. The trajectory is totally dropped. The student simply ignores the teacher for that entire round.
Wow.
It explicitly conditions every single parameter update on trajectory-level reliability.
It's essentially a mathematical system that teaches the AI how to be deeply skeptical of its own training data. It's exactly.
Which is philosophically mind-blowing when you think about it.
It really is.
But as with everything in Gen AI, theoretical elegance is one thing. Having established how this brilliant gate mechanism works, we have to ask the obvious question.
Does it actually work?
Right. Does it actually yield a smarter AI in practice?
Well, the researchers were incredibly thorough in proving this. They ran extensive experiments using the Quen 2.5 suite of models.
Okay.
They used a massive 14 billion parameter model as the teacher and a tiny 1.5 billion parameter model as the student.
David and Goliath.
Exactly. And they unleashed this gated setup on some of the hardest reasoning benchmarks available in the industry, specifically GSM-8K for complex mathematical word problems and MBPP for Python coding tasks.
And looking at the data, it absolutely crushed those benchmarks.
It really did.
The paper breaks down the specific stats. They tested RGOPD against standard distillation methods. To put this in perspective, they compared it to something called vanilla reverse KL distillation.
And just to briefly demystify that term for the listener.
Please do. Reverse KL divergence is essentially a mathematical formula used in distillation. It measures how much the student's probability distribution diverges from the teacher's and tries to minimize that difference.
Okay.
It's the standard way of forcing the student to mimic the teacher.
Got it. So compared to that standard mimicry, using a typical 1024 token generation length, RGOPD beat vanilla reverse KL by 2.9 points.
Huge improvement.
But they also tested it against a much more recent, highly touted baseline called TSD-KD, and it beat that by 4.9 points on average across math and coding.
Right.
This gated approach just builds a definitively smarter, more capable student.
It does. Though, to impartially report the data as it's presented in the paper, we should note there was one specific exception in the benchmarks.
Oh, what was that?
While RGOPD dominated in reasoning and coding, the TSD-KD baseline did retain a slight edge on a benchmark called IFEVL.
IFEVL.
Yeah. This benchmark specifically measures instruction following, how well the model adheres to formatting constraints or conversational instruction.
Yeah.
TSD-KD scored 54.68 compared to RGOPD's 48.60.
Huh. Why do you think that is? If RGOPD is so much better at pure math and deep logic, why does it lag a little bit on just following instructions?
Well, it likely comes down to the underlying architectural focus of the two methods.
Yeah.
TSD-KD uses a technique called entropy regularization.
Meaning?
Without getting lost in the weeds, entropy regularization is basically a mathematical way of forcing a model to keep its options open.
Okay, so it doesn't get tunnel vision.
Right. It prevents the AI from becoming too rigid or overconfident in one single robotic way of speaking.
Ah.
Because of this, TSD-KD is highly tuned to preserve the student's innate, soft conversational instruction-following behavior while carefully gripping in teacher guidance.
Okay, and RGOPD?
RGOPD, on the other hand, is ruthlessly, narrowly focused on pure reasoning accuracy.
Which might cause it to slightly overrate some of that softer conversational compliance.
Exactly.
That makes a lot of sense. It trades a tiny bit of conversational obedience for a massive gain in raw, undeniable logic.
Exactly right.
But here's where the results get really interesting.
Let's hear it.
If you look at Figure 2 from the paper, you see this fascinating evolution happening during the training process itself.
Yeah, this part is great.
As the training progresses over time, the students' responses get longer and longer. The average number of generated tokens just steadily climbs. The student literally learns to become more verbose.
Which is exactly the behavior you want to cultivate in complex reasoning tasks.
Right.
The student is naturally mimicking the long, deliberate chains of thought of the much smarter teacher. It's learning to think out loud, to break problems down into microscopic steps before rushing to a final answer.
Yes. And because the researchers noticed this newly acquired verbosity, they decided to run the benchmarks again.
Yep.
But this time, they gave the student a massive 8,096 token budget to think.
A huge budget.
They just gave it a massive blank canvas to work out the map, and the results were staggering.
What were they?
In this long generation setting, RGOPD outperformed the untuned student baseline by a massive 8.2 points.
That's incredible.
In the world of LLM benchmarks, an 8.2-point jump isn't an incremental improvement, it's a canyon. It's a night and day difference in capability.
It really is a remarkable leap. And while we're on Figure 2, there's another detail in that chart that is incredibly telling about how this system matures.
Oh, yeah.
They track a metric called the kept token fraction.
Kept token fraction. Okay.
This measures how often the reward teacher gate is actually staying open and letting the teacher's feedback through.
And what happens to that fraction as the student gets smarter?
It drops steadily. It goes from staying open about 90% of the time at the start of training down to about 70% by the end.
Wow. So it closes more often.
Yeah.
Yeah.
What this signifies is that as the student gets smarter and more capable, its own internal probabilities start to align more closely with the teacher's.
Right.
The likelihood gap between them shrinks.
So the gate naturally becomes pickier. As the apprentice approaches mastery, it relies on the master's advice less and less. It only accepts the feedback when the teacher has something truly differentiated and highly valuable to offer. It's a self-regulating system that naturally tapers off the training wheels.
It's beautiful in its efficiency. But moving from theory to engineering,
Okay, shifting gears.
there is a massive logistical hurdle to making all of this work. And it's hidden away in the appendix of the paper.
Oh, I love the appendix stuff.
Right. To achieve these performance gains, to constantly compare these likelihood gaps, the computers have to crunch an unbelievable amount of probability data.
Right, because let's think about the scale here. When we say the teacher and student are comparing likelihoods, we aren't just talking about flipping a coin.
No, not at all.
The AI's vocabulary contains tens of thousands of individual words or tokens.
Exactly.
For every single step of the reasoning process, the system has to calculate the exact probability for every single word in the entire dictionary simultaneously,
For both the teacher and the student.
and then compare them.
And doing that naively, computing that full vocabulary reverse KL divergence across tens of thousands of tokens is a computational nightmare.
Yeah, that sounds like it would melt a computer.
The memory overhead is astronomical. If you tried to run that on standard hardware, you would run out of GPU memory almost instantly.
So how did they fix it?
Well, the researchers had to implement a fascinating engineering trick to make this feasible. It's called the top K reverse KL approximation.
Okay, let's break down that approximation. How do they avoid crashing the GPUs?
Basically, instead of looking at the probability of all 50,000 words in the dictionary for every single step, they cap it.
Cap it at what?
They sort the probabilities and only look at the top 50 most likely words that the student is considering at that exact moment.
Oh.
In this equation, K equals 50.
Okay, capping it at 50 definitely reduces the computational load. But wait,
Yeah.
doesn't that introduce a huge mathematical blind spot? If you only calculate the probabilities for the top 50 words, you are completely ignoring the long tail of tens of thousands of highly unlikely words.
Yes. And even if they are unlikely in probability distributions, that ignored mass has to add up to something, right?
You've hit on the exact danger of the top K approximation. You do lose a crucial part of the learning signal if you just ignore that tail.
It's like grading a multiple choice test that has 1,000 possible options, but you only look at the top 5 most likely answers.
Right.
If you just pretend the other 995 answers don't exist, the math of the test completely breaks down.
That's a great way to put it.
So how do they fix it without running out of memory?
They use something called the tail correction.
Tail correction.
Rather than calculating the individual probability of all those 995 unlikely answers, they sweep all of that remaining unlikely probability mass into a single aggregate bucket.
Oh, wow.
Yeah, they create one miscellaneous category. The paper proves that bundling the tail into a single bucket and comparing that one bucket between the student and teacher preserves the integrity of the math without overloading the memory. That is such a clever workaround. And we know for a fact that it's vital because they ran an ablation study to prove it.
Right in table 2.
Yeah, in table 2 of the paper, they show what happens if you get lazy and drop this tiny tail bucket and just run the top 20 or 50 without it.
It drops.
The model's reasoning performance noticeably degrades. It drops from a 47.10 average score down to 45.50.
Exactly.
It proves that even the long shot, less than 1% probabilities carry a vital learning signal that the student desperately needs to see.
It highlights just how delicate the balance of information is during distillation. Every fraction of a percent matters.
It really does.
And speaking of how we measure these models, there's a fascinating detail in Appendix B regarding how they are evaluated.
Oh.
The researchers point out that using likelihood-based scoring is actually a terrible way to grade these instruction-tuned models.
How does likelihood-based scoring work compared to what we've been talking about?
So likelihood-based scoring is where you just ask the model to rank fixed, pre-written answer choices rather than letting the model generate its own free-form text.
Oh, I see. So it's like forcing the AI to just fill in the bubble on a Scantron test instead of letting it show its work on the whiteboard.
Exactly. And because these models were explicitly optimized for free-form reasoning and chain-of-thought generation, forcing them into a Scantron format yields bizarre results.
Bizarre how?
Well, the paper highlights a genuinely funny anomaly on the PsyQ likelihood benchmark. The giant, supposedly brilliant 14 billion parameter teacher model actually scored lower in 86.80 than the tiny 1.5 billion parameter untuned student, which scored in 89.50.
Wait, really? The master failed the pop quiz while the apprentice passed?
Yep.
That is incredible. It just perfectly illustrates why we cannot blindly trust these massive models as infallible oracles in every single format. They have their own weird quirks, formatting biases, and massive blind spots.
Which brings us right back to the central thesis of the paper, the absolute necessity of the reward teacher gate. You must have a mathematical system that independently verifies the outcome before trusting the guidance.
So as we wrap up, What does all of this highly technical source material mean for you listening right now?
The big takeaway.
Why should you care about reverse KL approximations, likelihood gaps, and reward gates?
Good question.
It matters because this paper is the blueprint for the immediate future of the technology you use every single day.
Exactly.
As a learner or professional who relies on fast, well-informed AI tools, you want models that are deeply capable but small enough to run quickly and cheaply.
And privately.
Right. Maybe you even want them running entirely locally offline on your phone or your laptop for privacy reasons.
Yeah.
RGOKD is the precise mechanism that will allow that tiny model on your phone to reason with the depth, nuance, and logic of a giant, warehouse-sized supercomputer.
That's exactly it.
And it will be able to do that because it was trained to actually understand the steps of logic, not just blindly parrot a larger model's hallucinations.
It represents a fundamental shift from rote memorization to verifiable reasoning. It's teaching the AI how to think critically, even about its own training data.
Which leaves us with a truly fascinating, lingering thought to ponder.
Okay.
We started by talking about the master and the apprentice and how this new training method encourages the apprentice to question the master.
Right.
If we are now successfully creating AI models with internal gates that actively evaluate when a teacher's advice is wrong and explicitly ignore that bad advice, could we eventually see a generation of AI students that systematically surpass their original massive teachers? Could this method of critical verified distillation eventually render those giant trillion-parameter foundational models obsolete simply because the smaller gated students outgrow them?
That's a profound possibility to consider. I mean, when the apprentice is no longer just a perfect mirror, but a critical, independent evaluator.
The limits of what they can learn are entirely rewritten.
Yeah.
The whiteboard is theirs now. Think about that next time you open an AI app on your phone. Thanks for joining us on this deep dive. We'll see you next time.